Hello everyone, welcome back to AEMPGO E123. This is assignment A. In this assignment, we are going to practice to use capacitor and inductors. P3.6. A 2000 microfarad capacitor, initially charged to 100 volts, is discharged by a steady current of 100 microamps. How long does it take to discharge the capacitor to 0 volt? So the question asks, how long does it take to discharge the capacitor? Well, we know that delta V over delta T is dV over dt. dV over dt is the rate. The current is discharged, and delta T is the total time used. Delta V is the voltage discharged. Well, so we have the voltage initially is 100 volts, but now the voltage is 0 volt. So we know that delta V is 100 minus 0, and the time is what we want to find out. So now we need to first look for the rate of the discharging. Now we know that the capacitance of the capacitor C is equal to 2000 times 10 to the negative 6 farads, and the current is a steady current with value of 100 microamp. Well, so how can we know dV over dt? We know that for capacitor, to calculate the currents, we have a formula I is equal to C times dV over dt. We know that I is 100 microamp, C is 2000 times 10 to the negative 6 farads, so we can easily find out that dV over dt is equal to 0.05 volt per second. Now we found this value, we substitute it back to this equation. We know delta V is 100 minus 0, that's 100, so delta T is equal to 100 over 0.05, that's 2000 seconds. Question P3.11. The voltage across a 1 microfarad capacitor is given the voltage Vt is equal to 100 e to the power of negative 100 t. So we have the capacitance of the capacitor is 1 times 10 to the negative 6 farads. The V is 100 e to the negative 100 t. And we need to find the expressions for current, power, and stored energy. And we are also asked to sketch the waveforms to scale versus time. Let's first calculate the current. We know that for capacitors to find the current, IT is equal to C times dV over dt. C is 1 times 10 to the negative 6 times dV over dt is, we take the derivative of this, that is 100 times 100, it becomes 10,000 times e to the negative 100t. And we simplify this, we can get IT is equal to negative 0.01 e to the negative 100t amp. So we found out the currents, and now we need to calculate the power. To calculate the power, we use the standard formula that's P is equal to V times I. We know the expression for V and the expression for I. We simply multiply them together. So that's 100 E to the negative 100t times negative 0.01 e to the negative 100t, and multiply this out and simplify it, you get negative e to the 200t watts. Well, lastly, we need to calculate the energy. So for capacitors, we have the formula that's W is equal to 1/2 CV squared. We know C is the value here, and V is the expression here. And we directly substitute all the numbers in, and you can get 5 times 10 to the negative 3 times e to the negative t joule. Form to scale of versus time, because we have exponential expressions, you can use plotting software like Desmos to plot the waveforms. Question P3.17. At t is equal to 5 seconds, the energy stored in a 10 microfarad capacitor is 200 joules and is decreasing at 500 joules. So we know that now the time is at 5 seconds. The energy W is the energy stored in the capacitor is 200 joules, and the capacitance is 10 microfarads, and the energy decreasing speed is 500 joules per second. Well, if you look carefully here, joules per second is actually the unit for power. So what it means here is that the power is 500 joules per second. The question asks us to determine the voltage magnitude and the current magnitude at t is equal to 5 volts. So for the capacitor, we have two formulas to find the voltage. The first formula is V is equal to 1 over C, and take the integral from T0 to T of I dt plus V0. Well, if we use this formula, we are not sure. We don't know the current, and the current is also something we need to find out. And we also don't know V0. So we cannot use this formula in this case. We also have another formula that involves the quantity voltage, that is W is equal to 1/2 CV squared. We know C, we know the energy consumed, that's 200 joules. We can find out V. So 200 is equal to 1/2 times C is 10 microfarads times V squared, and this is 10 to the negative 6. So we can solve that V is equal to 6,325 volts. Now we have found the voltage value. We also know the power, so we can easily find out the current. We know that P is equal to V times I. P is 500, V is 6,325 volts. So I is, because here the power is decreasing the energy, so we have the power as a negative value here. So I is approximately equal to negative 79.06 milliamp. Well, now we get a negative current value. What does a negative current means for a capacitor? Well, if the current value is negative, it means that the energy is decreasing. So so that the current flows in the opposite direction, and the current is flowing out of the positive end. Question P3.21. 28. Consider two initially uncharged capacitors C1 and C2. We have C1 is equal to 50 microfarads, C2 is equal to 10 microfarads, and they are connected in series. We also have a capacitor, we have a voltage source with a voltage value that's 50 volts, and all of these three are connected in series, as shown in this figure. So we need to find the voltage V1 and V2. V1 is the voltage across the capacitor C1. V2 is the voltage across C2. Well, we have a hint here that the charges stored on the two capacitors must be equal. So the charge Q for this and this are the same. The reason is very straightforward. It's because the current is the same for both of the capacitors. And if you recall the definition of the current, what we learned from the first week, we know that the definition of the current is dq over dt. So with the same current, we have the same capacitor stored for these two capacitors. So let's find out how to calculate the voltage V1 and V2. Well, to calculate the voltage for capacitors, we have two formulas. The first formula is V is equal to 1 over C, and take the integral of the current plus V naught. Well, for this formula, we don't know the current, so we cannot use the current to calculate the voltage. Therefore, we cannot use this formula. So let's recall our other formulas that we can use. Well, we know that the charge Q is equal to C times V. Q is the charge for the capacitors, and the capacitance value is C. We know the capacitance, so all we need is the charge. So now what our task becomes to find the charge value Q. Well, for this circuit, we can actually simplify it by combining these two capacitors. To combine these two capacitors, we know that for two capacitors connected in series, we can find its equivalent resistance as C1 times C2 over C1 plus C2. So we substitute in the 50 and the 10 into this expression and simplify it. You get 15 times 10 over 50 plus 10. You will get a CEQ equal to 6 microfarads. So we have a CEQ, and to find out the charge Q, we can use a C here. This is 6 microfarads. And for the simplified circuit looks like this. This is CEQ, this is 50 volts. Well, so for this circuit, we know the voltage value, that's 50 volts. So for this circuit, we can actually calculate the charge. So that is 6 microfarads times 50 volts, and this is equal to 300 microcoulomb. Well, and this is also the same charge value for the C1 and C2, so we can easily calculate V1 and V2. V1 is Q over C1, 2 is Q over C2, and substitute in this value here and here, and substitute this C1, the value for C1 and C2, you can get V1 is equal to 20 volts, V2 is 30 volts. Question P3.7, a constant current value of 3 milliamp, IT is equal to 3 milliamp, flows into a 50 microfarad capacitor. So C is equal to 50 times 10 to the negative 6. And we have the voltage at 0 at the beginning, V0 is equal to negative 20 volts. And we assume to use the passive configuration. We ask to find the power at t is equal to 0 and state whether the power flows into or out of the capacitor. And we ask to do this again when t is equal to 1 second. To calculate the power, we use the standard formula that's P is equal to V times I. And I is 3 times 10 to the negative 3 M from here. But to find the power, we also need to know the voltage. So for the capacitor, how should we calculate the voltage? We have a formula that's V is equal to 1 over capacitance, and take the integral of the current I plus V naught. Let's substitute in the value. And we simplify this expression, we can get 60t minus 20. Well, so the P is 60t minus 20 times 3 times 10 to the negative 3. So if we substitute in then t as t equal to 0, we can get P0 is equal to negative 60 milliwatts. P1 is 120 milliwatts. Well, because this is a negative value, so we can know that the capacitor is delivering energy. And this is a positive value, so it's absorbing or consuming energy. Question P3.14. The current through a 0.5 microfarads capacitor is shown in P3.14. At time is equal to 0, the voltage is 0. So originally there is no voltage. V0 is equal to 0. And then we are asked to sketch voltage, power, and stored energy to scale versus time. We mainly have 3 stages here. So let's sketch the voltage first. 2, 3, 5. For the first stage, Vt is equal to 1 over 0.5 times 10 to the negative 6. dt. Well, because here we use the millisecond, so we can times 10 to 3, and the final answer will be 40t. And in the graph, it looks like this. This is 80. Well, for the second stage, Vt is 0.5 times 10 to the negative 6. It starts from 2t, but the current is originally 0, so 0 dt plus at the start point, it starts at t is equal to 2, so here it is 80. And the value is 80. So from t is equal to 2 to 3, the voltage gives a constant of 80 volts. Lastly, Vt is equal to 1 over 0.5 times 10 to the negative 6. So t negative 0.02 dt. Then simplify this expression, you can get Vt is equal to negative 40 plus 200 So it looks like this. Now let's draw the power graph. Well, it's very similar. We have P is equal to V times I, and from this graph we know the I, and from the last question we know V. We just add them. We just multiply them together, and then you can get the power graph. Okay, so the first stage is 40t, and at t is equal to 2 seconds, it is 1.61. And between 2 and 3, because the current is 0, so the power is equal to 0. And then at this point, that's negative 0.2 times negative 40t plus 200, and the waveform looks like this. Similarly, you can plot the energy graph as like this. This is 2, 3, 5. W is equal to 1/2 CV squared. You can substitute the number into this expression and find W. Question P3.26. Find the equivalent capacitance between terminal X and Y for each of the circuits shown in figure P3.26. So let's see the question A. Terminals are here, X and Y. And we first need to find out which capacitors are connected in parallel, which are connected in series. And my recommendation is simplify from somewhere that's far away from the terminals. Well, for example, we can start here. We see that a 1 microfarad capacitor and this 1 microfarad capacitors are connected in parallel. So we can combine these two, and we need to recall how to combine the capacitors. Well, for capacitors connected in series, we have Q is equal to C1 times C2 over C1 plus C2. And if they are connected in parallel, we have C1 plus C2. That's the opposite of what we do for resistors. So here, if we want to combine these two in parallel, we directly 1 plus 1, that's 2 microfarads. But for these two connected in series, we need to have 1 times 2 over 1 plus 2. So that's 2 over 3 microfarads. Now let's redraw the circuit. The circuit would look like and this is 2 microfarads, and this is a 2. So now we see that 2 over 3 microfarads and the 3 microfarads capacitors are connected in series. So we directly add them together, and that's 11 over 3 for us. And these two are connected in series. So 2 times 2 over 2 plus 2, that's 1 microfarads. And now let's redraw the circuit again. We can see that these two capacitors are connected in parallel. So we have 11 over 3 plus 1. That's 14 over 3 microfarads. So the equivalent capacitance is 14 over 3 microfarads, which is approximately equal to 4.667 microfarads. Now for question B, we can see that this is node A, this is node B, and this is node C. So for the 2 microfarads and 1 microfarad capacitors are connected in parallel because both of them share node A and B. So we have 2 times 1 because they are connected in parallel here. So we directly add them together. That's 2 plus 1 is equal to 3 microfarads. And similarly for the 4 microfarads and 2 microfarads capacitors, we have 4 plus 2, that's equal to 6 microfarad. And now the circuit would look like this. So the two combined capacitors are connected in series. So we use 3 times 6 over 3 plus 6 is equal to 2 microfarad. So the equivalent resistance for question B, CEQ, is equal to 2 microfarads. Question P, 3.43. The current flowing through a 2 Henry inductance is shown in figure P3.43. And we are asked to sketch the voltage, power, and stored energy versus time. We have L is equal to 2 Henry. And we first need to find the expressions for the current for each stage. We have 1, 2, 3. We mainly have 3 stages here. So for each stage, let's write down as expressions for the current. So for the first stage, that's IT is equal to 30T. 2 is IT is equal to negative 30T plus 6. 3 is 30T minus 12. Well, so how can we find the expression for the currents? We actually can choose 2 points, and we can use y is equal to kx plus b. So we can find k and b by using the coordinates for these 2 points. Well, then we can draw the diagram for voltage. We know that for the inductance, Vt is equal to L times di over dt. So it's very straightforward to draw for the voltage. So let's see. For the first stage, V is equal to, take the derivative, that's 30, and times 2, 60. And similarly for the second, that's negative 60. For the third stage, that's 30. That's 30 times 2 as well. So that's 60. So we have the circuit. We have the diagram looks like this. Now let's draw for the power. Well, we know that for power, P is equal to V times I. And the expression for I is listed on the last slide. So we have for each stage, this is 0.1 and this is 0.3. For the first stage, that is P is equal to 30t times 60. So the diagram looks like this. For the second stage, that's negative 30t plus 6 times negative 60. For the third stage, that's P is equal to 30t minus 12 times 60. For the first stage, it should be 30t times 60. Yeah. So we can plot the graph like this. This is the first stage, second, and third. Finally, we need to sketch the stored energy. We know that for inductance, that is 1/2 times L times I squared. So for the first stage, this is 1 times 30t squared, that's 900t squared. For the second stage, that's negative 30t plus 6 squared, 900t squared minus 360t plus 36. And for the last stage, that is 30t minus 12 squared, and this is 900t squared minus 720t plus 144. So if you draw the circuit, you draw the diagram will look like this. This is 1.3. Question P3.50. The current flowing through a 300 millihenry inductance is given by 5 times the exponential of negative 20t m. So I is equal to this value, and we have the inductance L is equal to 300 millihenry. And we need to find an expression for the voltage, power, and stored energy, and sketch the waveforms. So let's first find out the voltage value. We know for the inductance, to find voltage, we have a formula Vt is equal to L times di over dt. L is this value, that's 0.3 Henry, and the expression for current is this one, that's negative 1000 e to the negative 200t. So we multiply them together, get negative 300 e to the negative 200t. So this is our voltage. And now we need to calculate the power. The standard formula to calculate the power is P is equal to Vt times It. And we know that Vt is here, and the expression for I is here. We multiply them together and simplify. We can get negative 1500 e to the negative 400t watt. And finally, we need to find out the stored energy. That's W is equal to L times I squared over 2. L is the value here. L is the value here. I is the value here. So we substitute in, that's negative 0.3 Henry times 5e to the negative 20t squared over 2. And the value is 3.75 e to the negative 400t. For the waveforms, with the potential expressions, you can use those plotting softwares to plot waveforms. We use the MATLAB. Question P3.60. Determine the equivalent inductance for each of the series and parallel combinations shown in figure P3.60. Well, for inductors, the combination rules are exactly the same as for resistors. So for inductors connected in series, we have the equivalent LEQ is equal to L1 plus L2. And for the inductors connected in parallel, that's L1 times L2 over L1 plus L2. Okay, so let's combine and simplify the circuit. So for the first circuit, we combine these two as 3 Henry. And then the 6 Henry and 3 Henry inductors are connected in parallel. So we have 6 times 3 over 6 plus 3, that's 2 Henry. Now the circuit becomes like this: 1 Henry, 2 Henry. So these two are connected in series again, and we can simplify them by adding them together. That's 3 Henrys. This is question A. Question B. We first combine these two connected in parallel, so that 18 times 9 over 18 plus 9. And this is 6 Henrys. And combine these two, that's 20 times 5 over 20 plus 5. That's 100 over 25, so that's 4 Henrys. So let's redraw the circuit. Now the circuit looks like this. This is 4 Henrys, and 6 Henrys, and 15 Henrys. The 4 Henry and the 6 Henrys are connected in series, so we can combine them to become a 10 Henry inductors. Now these two are connected in parallel, so we can combine them again. That's 15 times 10 over 15 plus 10. And the value is 6 Henrys. P3.45. A constant voltage of 10 volts is applied to a 50 microhenry inductance as shown in figure P3.45. The current in the inductance at t is equal to 0 is negative 100 milliamp. At what time Tx does the current reach 100 milliamp? So we have the voltage as 10 volt, that's a constant value, and the inductance value is 50 microhenry. The current in the inductance at t is equal to 0. 0 is equal to negative 100 milliamp. I final is equal to 100 milliamp. And we are asked to find the time Tx. Well, we know that for inductors, to express the current, we can use the formula. We know that the current right now is 100 milliamp. That's also 0.1 amp, and the inductance is 50 times 10 to the negative 6 Henry. So now what we need to find out is T. We know that the voltage is 10 volt and I naught is negative 100 milliamp. That's 0.1 amp. So let's simplify this equation. We have 0.1 is equal to 2 times 10 to the 5 T minus 0.1 amp. And we can solve for T. Then we can get T is equal to 1 times 10 to the negative 6 seconds. Question 3.51. The voltage across a 2 Henry inductance is shown in figure P3.51. The initial current in the inductance is I0 is equal to 0. Sketch the current, power, and stored energy to scale versus time. Well, so we know that the inductance value for the inductor is 2 Henry, and I0 is equal to 0 amp. And we need to find out the current, power, and energy. Well, to calculate the current for an inductance, we know that we have a formula I is equal to 1 over L, and take the integral of the voltage plus I0. And we mainly have two stages here. So let's draw a diagram. And this is 3, this is 6. So for the stage 1, when time is between t is equal to 0 and t is equal to 3, we have 1/2, substitute in the numbers here, times, take the integral of 10 dt, because it is 10 volts here, and simplify, we get 5t. So the first part is expression is 5t, the function is 5t, and this is 15. Okay. Well, similarly, we can calculate for the second part. So that's 1/2 times, now it starts from t is equal to 3. So from 3 to t times negative 10, this is negative 10 volts dt, plus I naught. The I naught is 15 volts for the stage 1. So let's write 15. And simplify this, you get negative 5t plus 30. So we can draw it as like this. Let's continue to sketch the power graph. And the power graph is very similarly, we know that P is equal to V times I. So we know that we can find the V and the I for each stage and multiply them together. And according to the expression we found, we can draw the diagram. Okay. So for the first stage, V is equal to 10 volts, and the expression for current is 5t. So we have 10 times 5t is 50t. So we can draw it like this. Well, for the second stage, we have the expression as negative 50t plus 30 times negative 10. And simplify this, you get 50t minus 300. And this is 150. And this is also negative 150. So this is our graph for energy. Finally, to plot the diagram for the energy, we have W is equal to 1/2 Li squared. L is 2 here, so that's I squared. So similarly, we can draw for these two parts. For the first part, I is 5t, so I squared is 25t squared. Is 3, and the value is 225. Now, for the second stage, I squared is equal to negative 5t plus 30, and we have a square, so that's 25t squared minus 300t plus 900, and this 6. So our graph would look like this.